Okay, welcome back to the series of lectures on transform calculus. And in the last lecture, we have evaluated Laplace and inverse Laplace transform of various special functions, and today some of these functions will be used to solve the differential and integral equations. Okay, so let's go for the application, and today we will continue with this by solving various kind of differential equations, mainly the initial value problems, boundary value problems, and also some integral equations. And let's see. So, I start with the general procedure. So, the general procedure is that first we take the Laplace transform both side of the given differential or integral equation, and the second step, after taking this Laplace transform, we will get either algebraic equation or ordinary differential equations. In any case, we will obtain an equation of the form the Laplace of y as a function of s from this transformed differential equation, transformed ordinary differential equation, or algebraic equation. And third step, we will apply the inverse Laplace transform to get the solution of the original problem. So, to get this y is Laplace inverse of f s. So, y is our unknown in the differential equation. So, there are basically three steps mainly. First, we take the Laplace transform both the side of the given differential equation, and then from the algebraic equation either we simplify that algebraic equation or we solve the ordinary differential equation, and we get this Laplace y is equal to the function of this s, and then at last we apply the inverse transform and we get the solution of the original problem. So, we will discuss anyway with the help of various examples today in this lecture. And let me just point out here that in the process we assume that the solution is continuous and of exponential order, because that is very important for the existence of Laplace transform. In fact, if our equation is linear and with constant coefficients, then one can prove that the solution is, under some assumption that the solution is continuous and of exponential order. So, whatever example here we will consider, in all of them we have the continuity in the solution, and the solution is of exponential order. So, we can apply this Laplace transform without any problem. So, let us start with the initial value problem. So, in this problem we want to solve the t 2 y over d t square plus y is equal to 1, and the given initial conditions are y at 0 and the first derivative of y at 0, both are 0. So, very simple initial conditions. So, while solving, as a first step we take the Laplace transform both the side of the equation. So, we have here Laplace transform of this y double prime plus Laplace transform of y and the Laplace transform of 1. So, by the derivative theorem, and that is the point that we can use this initial value problem. So, that this derivative theorem will help. So, here if we apply the derivative theorem, we have s square and Laplace of y minus s y 0 and minus y prime 0, that is the derivative theorem for this, and then we have Laplace of y and we have Laplace of 1, that is 1 over s. So, here this term is gone because this is 0 and this is also 0. So, we have simply s square plus 1 and Laplace of y, and this is equal to 1 over s. And let me just point out here that this Laplace transform technique is as well suited for solving the initial value problem actually, because here we have already used these initial values, the given initial values. So, that is what this is the best suited for initial value problems. So, here and now we get the Laplace transform of y. So, everything s to the right hand side. So, we have s and 1 plus s square, and now we do the partial fractions of this. So, we have simply in this case 1 over s, and then we have here 1 plus s square. So, if we have here s simply and the minus sign, so we will get 1 over s and 1 plus s square. And this is a trick to get the Laplace inverse basically by this partial fractions. So, we have 1 over s minus s over 1 plus s square, the Laplace of y. So, we take the inverse now, take inverse Laplace transform, and then we will get this y is equal to. So, the Laplace inverse of 1 over s, that is 1, and we know that the Laplace inverse of s over 1 plus s square is simply cos t. So, that is the solution which incorporate automatically the initial conditions, because we are using at some point all these initial conditions in the solution. Just one more point, that we have evaluated here the Laplace inverse of 1 over s and 1 plus s square by the partial fraction method, that we did here the partial fraction and then use this Laplace inverse to each fraction to get the Laplace inverse. But what we can also do, that using the convolution theorem, and we have discussed already in the last lecture. So, this is the convolution of the Laplace inverse of 1 over s and the Laplace inverse of 1 over 1 plus s square, that is. So, this is the convolution of 1 over s, that is 1, and convolution with this sin t, that is the Laplace inverse of 1 plus 1 over 1 plus s square. So, by this symmetry property, we have convolution 1, and this is nothing else 0 to t, the convolution integral, and then we have sin tau and the t minus tau. So, here is independent of t. So, we have d tau, and sin t will give us minus this cos tau and then 0 to t. So, we have simply 1 minus cos t, the same value what we obtained there. Okay, so, the next example, we solve d2y over dt square minus 6 dy over dt and plus 9y is equal to t square e 3t, and the initial conditions are y 0 2 and the y prime 0 is 6. So, slightly more difficult, because here the initial values are, and both the initial values are given. In the earlier example they were 0. So, our equation was much simplified after taking Laplace transform. So, here again we do the same steps. We take the Laplace transform of this first term d2y over dt square, and that is s square. Laplace transform of y we can also denote by this big Y s, and minus s y 0 minus y prime 0 and minus 6, and here we can again use the derivative theorem s y s minus y 0 and plus 9, and the Laplace of y, that is y s, and is equal to here the Laplace of t square e 3t. So, we use the first shifting property. So, the Laplace of t square is 2 over s cube, and then we have e power minus 3 t. So, the Laplace will be 2 over s minus 3 cube using the first shifting property. So, now we collect the terms of this y s. So, what we have s square from here minus 6 s and then plus 9. The right hand side we have 2 over s minus 3 cube, then here y 0 is 2. So, this 2 s will go to the right side to give us 2 s. Then here we have 6 and then y 0 is 2. So, we have plus 12 and minus 6. So, we get 6. So, that side it will be minus 6. Okay, from here we get this y s, and that is 2 over s minus 3. Here if we look at this, we have actually this s minus 3 whole square. So, when we take to the right hand side, here we have s minus 3 power 5 and 2 s minus 3 over s minus 3 square. Okay, so now the last step, we take the inverse Laplace transform to get the solution, and we have here y t then in this case. So, 2 and the Laplace inverse of 1 over s minus 3 power 5. So, we have to use again the shifting theorem, and that will give us e power 3 t, and this is for t 4, the 1 over s power 4 or s power 5. So, we have 1 over factorial 4, that constant will be accommodated here, and we have t 4 and e 3 t for this minus 3 for this shift. And similarly, here this is 1 over s minus 3 and that will be e power 3 t, again the shift theorem, or directly 1 over s minus 3, we know it is e power 3 t. So, our solution is then y t is, so here we have 1 over 12 and t 4 e 3 t plus 2 e 3 t. So, we get the solution. Again this incorporate the initial conditions we have. So, this was rather a simple differential equations, and now we will, and that is the main application of this Laplace transform. When the right hand side is basically a discontinuous function or rather complicated function is sitting there, then they are very difficult to solve. So, in the next example we will see when the right hand side, so solve y double prime plus y c and heaviside function t minus a. So, or unit step function. So, here this is a constant when t is greater than a is some positive, and this is 0 when t is less than a. So, and the initial conditions are given y prime 0, that is 1. So, again we take the Laplace transform both the side of the equation. So, we have s square y s plus, oh no sorry, minus s y 0 and minus y prime 0. Here we have plus y s, the Laplace transform of y, and then we have c, the Laplace transform of this I can directly write from the basic definition. So, since this is defined for a positive only, so 0 a to infinity, and it will be e power minus s t and d t. So, what we have here s square plus 1 and we have y s, here y 0 is 0. So, this term is gone then, and y prime 0 is 1. So, we have minus 1 here and is equal to c, and now if we integrate this e power minus s t over minus s, and as t approaches to infinity for this positive s, this will be 0. So, we have e power minus a s over s, or we have s square, or this we can take to the right hand side. So, we have y s is equal to 1 over s square plus 1 plus a constant and e power minus a s over s and s square plus 1. And now the last step, we need to take the inverse Laplace transform. So, inverse Laplace transform, and that will give us y t is equal to this, we know, that is sin t, the Laplace inverse of 1 over s square plus 1, and then we have a constant term here, and the Laplace inverse of this 1 over s square plus 1 and e minus a s. So, again here sin t plus a constant, and this the second shifting theorem, because e power minus a s is there, then we will be having a shift in t. So, what we will get, but first we need to know what is the Laplace inverse of this function. So, for that we need to first get the partial fractions of this. So, 1 over s minus again s over s square plus 1, and we have e power minus a s, and now we can do this. So, sin t plus c, and this is the shift theorem we will be using here. So, the Heaviside function t minus a will come, and the Laplace inverse of this with t minus a instead of t. So, we have here 1, there is no t. So, will be 1, because Laplace inverse of 1 over s is 1, and minus this is cos t, the Laplace inverse of s over s square plus 1 is cos t, but we have this shift here. So, we will get the cos t minus a. So, this is the solution of the given initial value problem. Now, in the next example, we will take even a more complicated right hand side of the differential equation, and that is y double prime plus 2 y prime, and 2 y is equal to delta t minus 3. So, this delta function, and we can easily solve this equation using the Laplace transform. So, the initial conditions, we have y prime 0 and y prime y 0 and y prime 0 both 0, just for simplicity, and the solution we can see then. So, we apply the Laplace transform both the sides of the equation. So, we have s square, the Laplace transform of y minus s y 0, and we have minus y prime 0 plus this 2, again the derivative theorem. So, s y s minus y 0 and plus 2, we have y s, and the Laplace transform of this delta function we have discussed in the last lecture, that is simply e power minus 3 s. So, what we have now, we collect the coefficients of this y s. So, we have s square, we have 2 s, and we have 2 from there, and that y s, this y 0, this is 0, this is also 0, this is also 0. So, we have this all other terms 0 and e minus 3 s. So, y s is 1 over this, we can also write s plus 1 whole square plus 1 and e minus 3 s. Now, we this we can get using the second shift theorem, but first we need to get the Laplace transform of this term 1 over s plus 1 square plus 1, and this is again the shifting theorem, the first shifting theorem, because s is shifted to s plus 1, because this is nothing else but the Laplace transform of sin t, but we have to use a shift theorem for this s plus 1. So, what we have, so note that the Laplace inverse of this first s plus 1 whole square plus 1 is using the first shifting theorem, it is e power minus t and the Laplace inverse of 1 over s square plus 1, and that is sin t. So, once we have this Laplace inverse e power minus t sin t, we can get the Laplace inverse of this function with this e power minus 3 s using the second shifting theorem. So, this will give us taking the inverse Laplace transform now of the y s, we will get y t, and that will give us e power minus t sin t is there, and then we will get shift in t. So, with h t minus 3, because here minus 3 is there. So, h t minus 3 e power minus t minus 3 and sin t minus 3. So, with the second shifting theorem, we have this solution when the right hand side is the Dirac delta function. So, these were the examples of initial value problems, and now we will go for when the initial conditions are not given. In that case also we can get the general solution. For example, we take this. So, find the general solution. The general solution of y double prime plus y e power minus t. So, no initial conditions are supplied here. So, we have to get this general solution now. So, the procedure is the same. So, we have to take the Laplace transform now. So, s is square and y s minus s y 0 minus y prime 0 and plus y s Laplace of y, and Laplace of e power minus t is 1 over s plus 1. So, what we have now here, s is square plus 1 with this y s minus s, let us call it y 0, a simple notation, and for this we call it y 1, these are the constants, and 1 over s plus 1. So, instead of giving this some numerical value here, we will continue the calculations with y 0 and y 1. This is the only difference, and we have then y s is equal to 1 over s plus 1 s square plus 1 plus s y 0 over s square plus 1 plus y 1 over s square plus 1, or y s, again we do the partial fraction here. So, we have 1 over s plus 1 and s minus 1 over s square plus 1. So, what we are getting here, s square plus 1 minus s square and plus 1. So, we get 2 here. So, to compensate that we have half and plus s y 0 over s square plus 1 and plus y 1 over s square plus 1. Now, we can take the inverse Laplace transform. So, inverse Laplace transform will give us now y t, and this is 1 over 2 Laplace inverse of so linearity property we can apply here. So, 1 over s plus 1, that will be e power minus t. Then we have again this half here minus half, and s over s square plus 1, that is cos t. Then we have plus 1 over s square plus 1. So, this is sin t. Here again we have y 0 and with this cos t, and we have y 1 and the Laplace inverse 1 over s square plus 1, that is sin t. So, we have half e minus t and plus here y 0, we can combine these two, y 0 minus half cos t and plus this y 1 plus half and this sin t. And this y 0 y 1 are arbitrary constants. So, here y 0 minus half we can put another constant, and this we can put another constant. So, this is the general solution of the given differential equation, that is y t is half e power minus t, some constant with cos t plus another constant and sin t. So, this was the example where we found the general solution of the differential equation, and now we continue for the boundary value problems. Instead of the initial value problems, we have the boundary value problem. Boundary value problem. So, in this case we have y double prime plus y is equal to cos t, and the conditions are given that y 0 is 1 and y at pi by 2 is 1. So, we do not have information of the first derivative at 0, instead of that we have the y at pi by 2 is 1. So, the procedure is the same, we take the Laplace transform here. So, s square y s minus s y 0 and minus y prime 0 plus y s Laplace transform of this y and the Laplace transform of cos t, that is s over s square plus 1. So, we have y s now here and here. So, with s square plus 1 and we have this y 0 is given, that is 1. So, we can use that. So, this we will take anyway to the right hand side. So, we have the s over s square plus 1 and we have plus s from here and we have plus y prime 0, which is not known at this moment. So, here we get then the expression for y s, this is s over s square plus 1 whole square plus s over s square plus 1 and plus y prime 0 over s square plus 1. And now, we can take the inverse. Before that, we let me just point out that wherever we get this s square plus 1 whole square type things. So, because we know that the Laplace transform of sin t is 1 over s square plus 1. So, we know that the Laplace transform of sin t is 1 over 1 plus s square, and also then Laplace transform of t sin t. By the theorem, we have this d over d s of the Laplace transform of sin t, that is 1 over 1 plus s square, and we get simply here 2 s over s square plus 1 whole square. So, this is the term which we can see here. So, if we take the Laplace inverse transform, that is y t will be here. So, the factor half will come. So, half sin t plus cos t and here plus y prime 0 and then sin t. Now, the question is how to get this y prime 0, but we have a condition here that y at pi by 2 is 1. So, we can use that condition to get this y prime 0. So, using the given boundary condition y pi by 2 is 1, we can have here y pi by 2, that is 1 and then half t. So, we have the solution once again t sin t. So, we will get here pi by 2 and sin pi by 2 plus cos pi by 2 from this, and then y prime 0 sin t. So, plus y prime 0 and sin t sin pi by 2. So, what we get here 1, then we have here pi by 4, this is 1, this is 0 and plus then y prime 0, because this is also 1. So, here we get y prime 0 is 1 minus pi by 4, that we can again substitute to get that y t is half t sin t plus cos t plus 1 minus pi by 4 sin t. So, in this way we can also obtain the solution of the boundary value problems. Now, the next category we move, and here up to now we had the linear equations with constant coefficients. So, now we will consider the differential equations when the constant of the derivative terms are not constant, but they are the polynomials. So, for example, solve this y double prime plus t y prime minus 2 y is equal to 4, and the initial conditions are given that y 0 is minus 1 and y prime 0 is 0. So, here this term the coefficients are are not constant anymore, but they are polynomial in T. The procedure is the same, but now this time we will get the ordinary differential equation rather than the simple algebraic equation. So, taking Laplace transform both the sides, what we get here s square y s Laplace transform of y minus s y 0 and minus y prime 0 plus the Laplace of t y prime, that is again the theorem we use when we have multiplication by t. So, d over ds and the Laplace transform of y prime minus 2 Laplace transform of y and 4 Laplace transform of 1. So, 4 over s. So, what we have now, first let us do this y s minus s and y 0 is minus 1. So, we will get plus s, this is 0. So, we have minus d over ds of Laplace of y prime. So, that is f y s minus y 0 by the derivative theorem 2 y s 4 over s. So, s square y s plus s minus, we differentiate here, it is a product. So, d over ds we will get s dy over ds and we will get minus y s. Here it is a constant term. So, d over ds will make it 0 and 2 y s, we have 4 over s. So, we take common this y s here also 2 y s. So, we have s square minus 3 with y s and then we have here minus s dy over ds. We have right hand side 4 over s and we have this take to the minus s to the right side. So, what we have the equation in dy over ds, ordinary differential equation, plus here 3 minus s because 1 minus sign will accommodate here. So, 3 over s and minus s, we have y s and is equal to, we are dividing by this s. So, we have 4 over and multiplying by minus sign. So, 4 over s square and plus 1. Now, this is the ordinary differential equation, linear equation. So, we will solve this. So, we get the integrating factor that will be e over e power 3 over s minus s ds, and this is just e power minus s. So, 3 over s log s. So, e 3 ln s minus s square by 2. So, this is, here we can again simplify, this will be just s cube and e minus s square by 2. So, the solution of that ordinary differential equation in y s will be s y s and this integrating factor e minus s square by 2, the integral, and the right hand side that we have here minus 4 over s square plus 1. So, minus 4 over s square plus 1, this integrating factor e square e minus s square by 2 s and a constant of integration. So, we integrate this. So, we have minus 4, this we multiply, we have s e minus s square by 2, the first term, then we have plus s cube e minus s square by 2 t s and a constant. So, this we can integrate because this differentiation of this is sitting here with a minus sign, we will adjust at this place. So, this is nothing else but the 4 and e minus s square by 2 minus, now here we have to integrate by parts. So, this 1 s we will adjust with this s e power minus s square by 2 to get this integral. So, we have minus this s square, the integration of s e minus s square by 2 will be e minus s square by 2 with a minus sign, that is here, and then minus, and then minus will come from that place. So, we have plus, and we have 2 s, the differentiation of this s square, and then again the integral of s e power minus s square by 2 will give minus, and that is adjusted here. So, we have s square by 2 and ds plus c. So, 4 e minus s square by 2 minus s square e minus s square by 2, and we have at this stage now again. So, we have minus 2, and this minus due to the integral will come with minus, and then e minus s square by 2 and plus c. Now, this and this will give us 2 e minus s square by 2, and we have minus s square e minus s square by 2 plus a constant. So, this is with y s and S3 e minus s square by 2. So, we get from here y s is equal to, so 2 over s cube, 2 over s cube minus 1 over s and plus this c over s cube and e s square by 2. Now, again we see this one constant here. So, what will happen to this constant? We have already used our initial conditions. Here there is a point that this y s, that is the Laplace transform of this y, and thus as a property, if this is the Laplace transform of a piecewise continuous and of exponential order function, then as s approaches to infinity, this must go to 0. So, as limit s approaches to infinity, this s goes to infinity, this y s must go to 0, and this is only possible if we see here e power s square by 2 sitting. So, if s approaches to infinity, this term will blow up, and then we cannot get the 0 as a result. So, this is possible only when this c is 0. So, due to this condition, we have that c must be 0. So, c must be 0. So, this term is gone, then we have y s is 2 over s cube minus s. Now, we take the inverse Laplace transform to get y t, and this is the Laplace transform of 2 over S3, that's simply t square, and we have minus 1. So, this is the answer. Okay. So, we take another example of a similar kind. So, here we have to solve the t y double prime plus y prime plus t y. So, here also we have variable coefficients, and this y 0 is 1 and y prime 0 is 0. Solution, again we take the Laplace transform. So, Laplace transform of this, because this t is sitting. So, we have minus d over ds by the property of Laplace transform, and the Laplace of y double prime plus the Laplace of y double y prime minus again d over ds and the Laplace of y, this is 0. So, minus d over ds, and we have here s square Laplace of y minus s y 0 minus y prime 0 plus s y s minus y 0, and we have minus d over ds, and we denote it by y s. So, is equal to 0. What we get here, y prime 0 is 0. So, this term will vanish. So, we have minus d over ds s square y s minus, and this y 0 is 1 plus s y s minus y 0 is 1 minus dy over ds is equal to 0. So, we simplify this. So, minus s square dy over ds minus 2s ys, and here we will get d over ds of s 1. So, minus minus plus. So, plus 1 plus s y s minus 1 minus dy over ds is equal to 0. So, we collect the terms of this dy over ds. We have 1 plus s square, let us multiply with the minus sign. So, dy over ds, then here we have minus s y s. So, s y s we have multiplied by minus 1, and this is anyway they cancelled each other, and then we have is equal to 0. So, what we get, the differential equation, it is dy s over ds is equal to minus s over 1 plus s square y s, and this we can easily solve. We take this to the right hand side, to the left hand side in the denominator. So, if we integrate that, we get ln y s is equal to, and here we will get this the differentiation is sitting there. So, with minus half and this ln 1 plus s square and a constant ln c in this form, because we will get rather simple form here, then ln c and divided by the square root of 1 plus s square. So, c over 1 plus s square square root, and here we have the ln y s. So, in this way we get the y s, this is c over 1 plus s square, and if we take the inverse Laplace transform, so we will get y t c, and in the last lecture we have seen the Laplace inverse of 1 over 1 plus s square, that was the Bessel function. So, j0 t. Okay, so what we have now? Now we have the initial conditions are, because this c appears now. So, what we can use at least that y 0 is 1, that is given. So, here we have this y 0. So, we have 1 c and j 0 0, and j 0 0 we know that is 1, and in this way c we get is equal to 1, because if you remember this j 0 t was just the series minus 1 r and t by 2 r 1 over factorial r whole square. So, the first term will be 1, and then on all other terms t appears, and as this j 0 will be 1. So, we have c 1. So, then the solution of that given differential equation is y t is j 0 t. Okay, so that was the differential equation with variable coefficients, and now we come to the integral equation. So, the integral equation, here also we can apply the Laplace transform to get the solution. So, integral equation. So, an equation of the form f t is equal to g t plus 0 to t k t u f u d u, or we can have other forms. So, k t is just equal to this integral k t u and f u d u. These equations are known as integral equations. Integral equations, where this f t is the unknown function. So, here this f t is unknown, here f t is unknown. So, there is a special situation that when the kernel, this is called the kernel of the integral equation. So, if this kernel k T u is of the particular form that this k T u is just a function of t minus u, then the equation can be solved using the Laplace transform, and we will see why, because it will simplify that integral which appears in the integral equation. So, if we want to solve the integral equation f t e minus t square plus 0 to t sin t minus u f u du. Solution. So, if we apply the Laplace transform to this equation, we will get the Laplace transform of this f t, the Laplace transform of e minus t, this is e minus t, not t square. So, e minus t, this is Laplace transform is 1 over s plus 1 and plus. So, now if we see, this is the convolution integral. So, the convolution of this sin t and f t. So, if we take the Laplace of this convolution, it will be just the Laplace of the product. So, the Laplace of sin t and Laplace of f t by the convolution theorem, and this is the point here. Now, it gets simplified. So, we take the Laplace transform for f t, then so Laplace transform of f t, and we have 1 minus this Laplace transform of sin t, we know 1 over s square plus 1, and we have 1 over s plus 1 right hand side. So, we get Laplace of f t is equal to the s square plus 1 minus 1. So, we have s square. So, this is nothing else, the right hand side we can take s square plus 1 over s square and s plus 1. Again the partial fraction. So, this step I skip. So, you have we have here 2 over s plus 1 and plus 1 over s square and minus 1 over s. Now, we can take the Laplace inverse. So, we have 2 over s plus 1, that is 2 e power minus t, 1 over s square t and then minus 1. So, this is the solution of that integral equation. Now, I will consider a different example where we will see the integral terms as well as the differential term, and that is called the integral differential equation. So, I will take here one example just for the to make the concept clear. So, we have here the integral differential equation dy over dt plus 4 y plus 13 and 0 to t, we have y u and du, this is 3 e minus 2 t and sin 3 t, and y 0 because the differential term appears. So, we have to have the initial condition, that is y 0 is given 3. So, now we go along with the same steps. So, we have the Laplace transform. So, here we s the Laplace transform of y and minus y 0 plus this 4 Laplace transform of y and plus 13 and Laplace transform of this integral, and that is just the 1 over s and the Laplace transform of this y. That was a property we discussed in the Laplace transform. Then we have 3, and then we have the first shift property e power minus 2 t and sin 3 t. So, for the sin 3 t, the Laplace transform is 3 over s square plus 9, but we have this shift here. So, we have 3 over and s plus 2 instead of s because of this e power minus 2 s square and plus 9. Now, we collect the terms of this ys over s is here. So, we will get s square, and then we have here also 4s, and then we have 13, we have over s, we have ys, and this y0 is 3. So, we can take to the right hand side. So, we have s plus 2 whole square plus 9 and plus we have this y0, and that is 3. So, we simplify this to get ys will be 9s, and this is again the same term because this is s plus 2 whole square. So, we have 4 and then 9. So, it is the same term. So, we get basically s plus 2 whole square plus 9 and the square, and plus we have 3 over s plus 2 whole square plus 9. Okay. Now, we take the inverse Laplace transform, and just remember again the shift property, because here s is s plus 2. So, let us apply the shift property. We will get e minus 2t and then Laplace inverse of 9 s minus 2 over s square plus 9 whole square plus 3 over s square plus 9. So, s is now s minus 1. So, we have here s square s minus 2, and here we have s square plus 9. Now, to get this Laplace inverse, we should note that the Laplace transform of t sin a t is 2 a s over s square plus a square, just minus d over ds of sin a t, Laplace of sin a t. Similarly, the Laplace transform of t cos a t is s square minus a square over s square plus a square whole square, because this whole square term is sitting there. So, we have that ys as e power minus 2 t, and the Laplace inverse of 9 s over s square plus 9 whole square. This is straight away we will get sin 3 t. We have minus 18 over s square plus 9 whole square, and we have 3 over s square plus 9. So, here we get this from the sin a t, we need to have here s square minus a square term. So, 2 t, we have L inverse, this 9 s we will keep it, and this 3 we will take 1 over s square plus 9, we will combine with this, and what we will get, because 1 over s square plus 9 will be s square plus 9 by s square plus 9 whole square. So, we will get simply in this case s square minus 9 here over s square plus 9 whole square, and plus this 2 over s square plus 9, because 1 over s square plus 9 we have combined with this term. So, what we get e power minus 2 t, and the L inverse of this is easy now, it is a given form 2 a s over s square plus a square by 2. So, this is simply 3 by 2 and t sin 3 t. Here we get t cos 3 t, and here we get 2 by 3 and 3 then sin 3 t. So, this is the solution. The last example we consider quickly, and that's a simultaneous differential equation. I will just give the idea how to solve the simultaneous differential equation. So, in this example we take a very simple example, dx over dt 2x minus 3 y, and we have dy over dt, that is y minus 2x, and the initial conditions must be given that x 0 is 8 and y 0 is given 3. So, what we do, the same steps, we take the Laplace transform of these two equations, we take the Laplace transform of this equation. So, denote by big X s s minus x 0 and 2 x s minus 3 y s, and for the second equation we have s y s minus y 0, we have y s minus 2 x s. So, now from the first equation what we have s minus 2 x s, x 0 is given 8. So, we will take to the right hand side and this 3 y s, and then we have 8, let us call it equation 1, and from this equation we will get this y s 2 x s, 2 x s, and we get the s minus 1, this s minus 1 y s, and is equal to 3. That is equation number 2. Now, we need to solve these two equations, and I will skip that step. It is very easy that here we multiply by s minus 1, for example, here we multiply by 3, then we can cancel this y s term, we can eliminate this y s, and we can get this x s 8 s minus 17 over s minus 4 and s plus 1, and we get this y s, we get this y s 3 s minus 22 over s plus 1 and s minus 4. And now, we can take the inverse Laplace transform of in both the cases, again the partial fractions we have to do, and we will get straight away 5 e power minus t plus 3 e 4 t, and this y t we will get 5 e minus t and minus 2 e 4 t. So, it was just a just an idea how to solve this, how to apply this Laplace transform for the system of equations. And now, I conclude this lecture. So, in this lecture we have seen that how we can apply this Laplace transform to the various kind of differential equations, and we have mainly discussed the various initial value problems, boundary value problems, how to find the general solution, and then integral equations also for the integral differential equations, and at last the system of differential equations. So, and the last in the next lecture we will apply we continue this idea for solving the partial differential equations, and that is all for today's. Thank you. Goodbye.